Hello all, let's start section 3.1. Our section 3.1 or chapter 6 is functions. This is a very important topic that we start in chapter 3, functions. It's all chapter 3 is about functions, and to be honest with you, after this chapter, every day we are talking about functions. Then it's good to know what is a function, learn the definition, and understand what is a function. And for this purpose, I added also a PowerPoint presentation for chapter 3, and I'll do also a video lecture. I know most of you are familiar with the definition of function. You already did some operations on functions, but I'll start again like your book from the beginning, from the definition of a function. What is a function? It's really important to know what is a function. I will write the definition first for you, then I'll explain it maybe in a very simple language, because the definition is kind of complicated. If we have, or let's say let A and B be two non-empty sets, correct? A function from A to B is a rule of correspondence that assign to each element in set A let's underline this part, it's important, exactly one element in B. I'll put double line here because that's very, very important. I copied this definition from your book. If you have two sets that they are not empty and they have some elements in them, if I name set A and set B or X or Y, function is a rule that assigns an element in set B for set A. Or let's find an easier definition for function. Some people say function is a relation. It's really a good definition for function, but incomplete. Function is a relation. This part, relation, let's discuss what does it mean. Because if you see the definition in your book that I copied here on the board for you, actually that definition is talking about a relation. Look at this table. You use this table a lot since you start grade 7 in school to graph different functions. On one side we put x, on one side we put y, correct? Let's write a very easy equation in here, even I'm not naming it function yet. Y equals x plus 2. If I have some elements for x which I choose, for example, -1, 0, 1, and 2, if I plug in these values of x in my equation, definitely I can find the value of y, correct? For example, when x is -1, -1 plus 2 gives me 1, correct? When x is 0, 0 plus 2 gives me 2. When x is 1, 1 plus 2 gives me 3. Then y becomes 3. And when x is 2, y becomes 4. Correct? You see here a relation. When x is -1, y is 1. When x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. We call this one before for you an order pair. Right now I'm telling you an order pair is a relation. Each order pair represents a relation. Correct? Now, if I change this table and write all those values in two sets, for example, this, let's call it circle, is one set. This circle is another set. Let's name this one set A or X or whatever, or maybe X, correct? Call this one set B or Y. When X is -1, it's an element for set A. And set B, Y becomes 1. When X is 0, and set B, Y becomes 2. When X is 1, and set B, Y is 3. When X is 2, and set B, Y is 4. You see here a relation between two sets, set A or X or whatever you name it, and set B or Y or whatever you name it. There is a relation here. You see, if I kind of zoom out a little bit, my page, I know it gets smaller, but just for a minute to read the definition. A function from A to B. A function from A to B. A function from A to B is a rule. What is the rule? This is the rule. Is a rule of correspondence that assigns to each element. Or in a simpler language, function is a relation. Which kind of relation? That each element that each element of set A has only one correspondent in set B. That's why I double underline the last part of the definition. exactly one element in set B. Look, I'll show you another sets here, two sets. One set, another set. For example, C and D. Here, for example, x1 and 2. In D, I have 3, 4, and 7. When x is 1, when C is 1, 1 goes to 3 and 4. It has 2 elements in set D. When it's 2, it becomes 7. Such a relation, if one element of one set has 2 correspondents on the other set, you cannot call it a function. That's not a function, not a function. Why I'm emphasizing too much on this definition? Because starting today, if you go to calculus 1, 2, 3, or math 211, 212, 213, linear algebra, even statistics, differential equations, or even physics, even chemistry, even biology, every day you are dealing with functions. And if you don't know really the definition of function, then how to deal with those functions? I hate those type of lectures that I just put, oh, this is a function, f of x equals 2x plus 4. Let's evaluate f of 1. And no one knows what does it mean, why f of 1, why I'm doing this. Why? We are struggling with the mathematics because we never got the definitions. We never understand why we are doing this. What is this? Let me tell you, in our real life, everyday life, we are dealing with functions. Actually, our life is like a function. I can give you an example. You study 1 hour per day, you end up to getting a C in the test. If you study 3 hours per day, you may end up to get an A on the test. You see, it's a function, it's a relation. In 1 hour, or you're doing a job, you're working somewhere, you're working 2 hours per day, they pay you like $50 or $40 or $30 or minimum wage, maybe $24, something like this. But if you work more hours, they give you more salary. It's like function. It's working as a function. Or your calculator, your fancy calculator that every one of us, we love our calculators because calculator makes our life really easy. Calculator is working based on functions, correct? Then it's really, really important to know the definition of a function, because to avoid also mistakes when we are dealing with functions later on, correct? Then how to explain a function? A function is a relation. Which kind of relation? That each element of one set, or let's name it set X or A or whatever you name it, has only or exactly one element on set B, like this. This one is a function, but this one is not. Let me show you another example, another way to explain this. I know sometimes I'm talking too much, but I want to make sure that you know really what is a function. Let's say two cars are driving in one road, and this road separates to two different roads like this. And the other way, two cars are driving in two roads, and these roads are merging to one road. For example, your professor, Professor Ahmad, he has a kind of very fancy car from 1940s. He's driving this car. Is it possible for me to drive my car at the same time to both of these roads? When I reach to this point, go to this road and go to this road, is it possible to do at the same time? The only way is to cut my car in two pieces, send half of my body to one road, another half of my body with my car to another road. It's impossible. Look, if I name myself X, and if I name these roads Y's, one X cannot go at the same time to two Y. It's this case, one X, two Y's. Then this diagram or this example does not represent a function. But look at here. Two fancy cars are driving in two roads. Is it possible for them, for both of them, to go at the same time to one road? Definitely yes. The good example is when you are merging to a freeway. You are coming from a road and you merge to freeway and the other cars are also coming. It's possible. This represents a function. But this one is not a function. Correct? Hope it will be clear for you now what is a function. If I illustrate a function like a machine, a very simple machine for you, which your book did also, in many books we want to represent a function like a machine for you to show as a simple machine how a function is actually working. Look, if I draw a very simple machine here, for example, this is my machine. Whatever the shape is. Think this is your calculator. When you enter a value to your calculator, for example, 4, and you press the square root button in it, you get an answer 2. Is it right or wrong? Correct? When you enter a value, we call it input. When we get a number back, the result, we call it output. This one, the sign that I used in this example, that's the rule. That's the rule that you assign for this number. Function is working like this. You have input, you have output. In a table that I draw for you at the beginning, xy, and I use, for example, -1, 0, 1, and 2, and you had some values here, I don't remember, it was 1, 2, maybe 3, and 4, like this. X is your input. You saw your equation was y equal x plus 2. You plug in -1 here. It's your input. Then you use equal sign, output is 1. Correct? Y is your output. Input, output. Correct? Functions are working like a machine. You have input, you get output. Or I told you, you study 1 hour, 1 hour studying, this is the machine, this is through the semester, some rules are assigned for you to study, You study only 1 hour, the output, maybe a C or F. This is your grade. Hopefully no one does this. I study 5 hours per day. Oh, I'll end up with A+. Output is a good grade, the highest grade in the class. Now, few more things that I want to explain here, even before jumping to representation of a function. Let me talk about something else also here, because this is the first day. I want to talk everything here for you, correct? Then we move on. Maybe you see the book, you see my lecture. There is a difference between my lecture a little bit and your book. I'm trying to talk in a simple language with you, correct? I never assign to you, oh, go read your book. Yes, read your book. There are some classes, just read the book, do the test. No, listen to my lectures also. In both examples that I had XY, I usually use XY because you see a lot after this X and Y in your book A and B, but soon they will talk about X and Y. -1, 0, 1, and 2. I like this example because it's really easy. 1, 2, 3, and 4. I named this one input, this one output. Or if I draw two sets like this, this is X, this is Y, this is input, this is output. -1, 0, 1, 2. Here you have 1, 2, 3, 4. When X was -1, Y 1, 0, 2, 1, 3, 2, 4. We call input, when we are dealing with functions, we call input domain. I write a very bad D here. Let me erase the D. I didn't like it. Domain. We call the output range. I'm teaching a lot of classes, more than 25 years now. And every time that I'm discussing function with my students, most of them, they're struggling with understanding of what is domain, what is range. Domain is always your input. Range is always your output. If you see in a graph this, if you see in a graph, when X is -1, this is X axis, this is Y axis, right? When X is -1, Y is 1, this point, 1 and 1. If I show as an order pair, -1 and 1, an order pair, right? When X is 0, Y is 2. This point is 0 and 2. When X is 1, Y is 3. 1 and 3 maybe somewhere here. And if you connect all these points, they come under one straight line, on the one straight line. This is the graph of Y equal X plus 2, the equation that I put for you. What is your input, or what is your domain? Your domain is the values of X axis. What is your range? Your range is the values of Y. Correct? That easy. domain input, range output. Now, later we will discuss how to identify or how to determine the domain of a function. I will discuss it soon, maybe in the next 10 minutes. But even before going to there, let's talk generally about functions. Then we can discuss how to find the domain of some functions. Correct? How to represent a function, or ways to represent a function. Correct? There are four ways to represent a function. Number one, algebraic way. Algebraic. When I'm talking about algebraic, means this, the equation that I used for you, y equal x plus 2, or f of x equals x plus 2. Correct? This is the algebraic way that represents a function. Usually for equations, we write this way. When we talk about functions, we write this way. Later, I'll talk about notation. What is the notation and what is the meaning of notation? You represent a function. You can represent a function in an algebraic way. The second way that you can represent a function is verbal. What is verbal? All those word problems, most of them representing a function. Correct? For example, the area of a circle is directly, or the area of a circle is increasing when the radius is increasing. Area means this, right? If I have a bigger radius, I get bigger area. If I have a smaller radius, I have a smaller area. Correct? They put a word problem or an application for you, but that also can represent a function. Number three, table. Correct? A table can represent a function. Remember this table that I just used, xy, and I used values? Or a better example, if I give you a table of salaries in different years. It's a good example in your book. Here you have year. Here you have minimum wage. Minimum wage. For example, in 1975, the minimum wage was $2. In 1980s, the minimum wage was 3.1. In 2010, like so on. In 2010, the minimum wage, I remember this one because even not 2010, I moved to US in 2013. The minimum wage was 7.25. Right now, I don't know, what's the minimum wage? 14, 15, something like this? It's the minimum wage. You see, a table can also represent a function. Your salary or minimum wage is a function of time. In calculus, we discuss a lot. In physics, we calculus a lot. For example, position function. Those of you that you already had physics. Position is a function of time. Acceleration, function of time. Volume is a function of time. Correct? Even area can be a function of time in some problems in physics. Correct? Number 4, or the fourth way to represent a function, graph. I already draw a line for you. A graph can represent a function. For example, if I graph this minimum wage for you, here, dollars are your wage. Correct? Here, years or time. 1975. If I choose 0 as a 1975, the minimum wage was 2.0. Correct? In 80s, the minimum wage was 2.5 or 3. Correct? For example, if I name here 3.0, this was your minimum wage. And so on, 2010, the minimum wage was, what was, how much? 2010, it's kind of 7.5. All these dots that you see, it's actually a graph. It goes like this. It's a graph, only dots. Or in this example that I draw a line for you, that line represents a function. Later we will discuss, you draw a lot of lines before. Everyone is talking about the slope, the formula for the slope. And everyone is thinking, why always we are graphing line? Where I'm using it in my life, should I draw every day a straight line? Soon in this book and in Calculus 1, you understand the meaning of slope. What is slope? Slope is the average rate of change. We explain the slope in a different way to you. Slope is the average rate of change, or later, instantaneous rate of change, which Sir Isaac Newton started working on. That was the beginning of the idea of writing calculus. Sir Isaac Newton was looking to find the instantaneous rate of change, not just the average rate of change. That idea pushed him to write calculus. And to be honest, calculus changed the world. What we are using today, what technology we are using today, where we are today in our life, it's all because we know calculus. Maybe it looks crazy when I'm talking this way because I'm teaching math. Oh, he's talking too much about math. It's not that way, but believe me, whatever you see around you in real life, including your beautiful, expensive cell phone, that you're all the time busy with, it's because of mathematics. You have it. Correct? Anyway, there are 4 ways to represent a function. Algebraic way, verbal way, by table, or by graph. And these 4 ways you can represent any function. Any function actually can represent in 4 ways. Now, I discussed a little bit about the domain and range. What is domain and range? Domain is input, range is output, right? Now, how to determine the domain and range of a function? Even before that, let me add one more thing. Because we talk about the graph, it's not in your book, because your book is pre-calculus. The author of this book is thinking that you already know functions, but it's kind of review here. But because I talk about graphs, let's understand which type of the graphs we can call them functions. Can we call all the graph functions? Or some of them maybe not? Or we should call all functions? I don't know. Let's learn how to know if a graph represents a function. For example, I gave you a straight line here, and I'll give you a parabola, this shape, U shape, or a V shape maybe. Right now, a U shape. Are these 2 graphs, they're representing a function? To understand that a graph is representing a function, we have a method that we call it vertical line test. A very easy test. If someone gives you a graph and tells you, is this graph represents a function? Immediately do this. Draw a vertical line and different parts of your function. For example, here. If your vertical line only and only intersect the graph once in one point, that graph represents a function. You see, when I draw here, this red line, vertical line, only it intersects this line at one point. Or if I draw here, again in one point. If I draw here, again in one point. Or in this parabola, if I draw here, only in one point. If I draw here, only on one point. In some of my lower classes, sometimes when I teach the lower classes, the beginner algebra or intermediate algebra, I'm talking different way. But here for you, because you're a pre-calculus class, actually when you draw a vertical line, when you do the vertical line test, look at this order pair. For example, here you have an x. For example, -2. For example, I don't know exactly what's the value. For each x, you get only one y. Here, it's maybe 4. Here, if x is +2, you got y4. And if you want to draw this actually, when x is -2 and when x is 2, y is 4. It's the example that I draw for you. 2 cars can go at the same time in one road. Yes, this is a function. If it was like this, -2 goes to 4 and -2 goes to 6, that's not a function. Vertical line test is actually the shortcut of this. Look at this graph. I draw a circle for you. If you do a vertical line test, you intersect the graph twice, more than one time, then this is not a function. This is not a function. And algebraically, if you want to see, for one x, you have two y's at the same time. For example, when x is 1, y is 2, and y is negative 2. If you want to draw this, when x is 1, y is 2 and negative 2. 1x goes to 2y. That's my car. I cannot go at the same time to two roads. I cannot be in two classes at the same time. I can only be in one class. But I can teach different classes in different times. Correct? Now, how to identify a graph, a given graph, that it represents a function or not? Immediately do a vertical line test. If your vertical line intersects the graph only once, that represents a function. But in different part of your graphs, okay? Not just in one part. For example, like this. If I give you a graph, something like this, and you draw a line here. Oh, professor said do a vertical line test. Yes, here is the vertical line test. Only 1 point. Yes, this is not a function. But did you check this side? You have to do multiple tests in different points of the graph to know if your graph represents a function or not. Now, you're done with the basics, at least with the definition. Let's start this topic, which is determining the domain of a function. Of the domain of a function. Let's erase this off. I don't like it. Determining the domain of the function. If I give you a function, for example, y or f of x equal x plus 2 or y equal x plus 2, two ways. Later I'll explain why f of x. If I give you y equal, let's even for time being erase this one because I didn't talk about f yet. Y equal x plus 2 and ask you what is the domain and range of this function, how to understand what is the domain of a function. Few notes, few easy notes. At least one here. Domain of polynomial functions is always from negative infinity to positive infinity. You may ask, what is this? What's the domain from negative infinity to positive infinity? I will explain it in a graph for you. Why the domain is from negative infinity to positive infinity. Correct? Before we graphed y equals x plus 2. Correct? and the graph was something like this, right? I don't want to put all those values. I will talk generally about this function. This is y equal x plus 2. And we discussed the input, which is the values of x-axis, or the values of x. We call it the domain. Why the domain of, and this is a polynomial function, right? You know already the definition of polynomials. What is a polynomial? If not, please find an elementary algebra book or intermediate algebra book or search it online. They will give you the definition of polynomials. What is a polynomial? Correct? This is a polynomial function. Now, the domain is from negative infinity to positive infinity. Do you see these arrows that I draw in the two sides of this line? It means this line goes this side and never stops, continues going, and on this side continues going. Look, here for example, when x was negative 1, y was 1, right? When x was 1, y was 3. Now, if you add more and more and more and more and more values of x, right, you see, you get more values for y. And it doesn't end. It goes this way forever, right? Forever for us means infinity. When when x goes to infinity, also on this side, you see it continues to go to infinity, to negative infinity, right? You have values, 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 up to where? Up to negative infinity. And we already told you that the input is the domain, or values of x. Let me tell you another thing. The values of x is always your input. The values of y is always your output or range. Now, if I ask you, what is the domain of this function? The domain of a polynomial function y equal x plus 2. Your domain, if I use it a d just for domain, is from negative infinity to where? To positive infinity. You already saw the domain is from negative infinity to positive infinity. Correct? Polynomial functions, they are really easy to talk about their domain. You can see it immediately and you can understand what is the domain of polynomial functions, correct? Just read the values of x from where to where. That's your domain. But look at this example that your book immediately start with this example, even before explaining. Y equals a square root of 2x plus 6. What is the domain of this function actually? Can I say the domain of this function is also from negative infinity to positive infinity? Before to show you how to find the domain of function like this, which we call it the square root functions or radicals, before explaining the actual method for you, let me show you something. Let's use a table and see what you can see here in this table. For example, let's start from negative 4, then negative 3, then negative 2, then negative 1, 0, 1, and some more, 2. Let's plug in these values of x in this function and calculate the value of y. Y equals the square root of 2 times negative 4 plus 6, which gives you a square root of negative 8 plus 6, which gives you the square root of negative 2. Look at here. Under the square root, a negative number. I know you say, oh, yes, we can take the square root of a negative number. Totally agree with you, but that's imaginary, right? Remember, we rewrite this as a square root of negative 1 times 2, and we call negative 1 I, right? Then it's I radical 2. It's not a real number, it's an imaginary number. Then negative 4 is a problem. If I plug in negative 4 there, I cannot show where is I radical 2 on the number line. Can you show me on a number line where is I radical 2? We don't have that number on the number line. It's imaginary. We name it imaginary. Or some people, they call these numbers complex numbers, remember? Because it has two parts, the imaginary part and the real part. I hope you had a intermediate algebra class or college algebra class. It's not on the number line, then negative 4 is a problem. Correct? I have to remove this from my list, from X. It means I have to remove negative 4 from domain. Or in a better mathematical language, I have to restrict my function. You heard this word a lot from your other mathematics professors. Restriction. This is the meaning of restriction. You have to restrict your function. Correct? But if you plug in I will not plug in all these values. I'll just show some of them for you. If I plug in here, for example, negative 3, it will be negative 3 times 2 plus 6, which gives you negative 6 plus 6 under the radical, right? And if it gives you 0 and the square root of 0 is 0, I'm okay here. If I plug in 2, I'll be okay. Negative 1, I'll be okay. 0 even is okay. 2 is okay. Up to where? Up to infinity. Any number starting from negative 3 to infinity that I plug in this function, I can get a good output or a range. And why? It's real. But less than negative 3, problem. You saw one of them, for example, negative 4. If you plug in negative 5, you end up with negative 4. What's the square root of negative 4? 2i, not 2. Oh, not 2, but 2i. It's imaginary. Then, some functions, they have restrictions. And if someone asking you to find the domain of the function, you don't want to go this way. That's totally a crazy way that I explained for you. Do not use this way, please. Oh, I want to write the domain of this function right now. I know the domain of this function starts from negative 3 and it goes to infinity. That's the domain. That's my domain. Don't do this. It's so difficult to do this. I'll give you now an easy method how to find the domain of some functions, correct? I'll take the same example. Y equals the square root of 2x plus 6. To find the domain of, or to write the domain of this given function, what you do first? First, you find your restriction. How to find restriction? Whenever you are dealing with the square root function, make a note. When you want to find the restriction in the domain of a square root function, we call whatever is written under the square root, we call it radicand, right? Set your radicand greater and equal to 0. What does it mean? Greater and equal to 0. It means under the radical, it can be 0 because the square root of 0 will become 0. And positive numbers, they have a square root but not negative number. That's the explanation. That's the meaning of greater equal. Why you are making the radicand or under the radical greater equal to 0 and you find the domain. Look, when you set this, solve it. We already discussed how to solve an inequality. Solve it. Subtract 6 from two sides. These two cancels out. 2x greater equal negative 6. Divide by 2. These two cancels out. X should be greater equal negative 3. If you see your number line, that is negative 3. Greater equal negative 3. For negative 3, you use a bracket because you have a greater equal sign. And which side? You go to where? To infinity. Okay, here you go. Negative 3 comma infinity, your domain. That's the domain. I think the shape of this graph should be something like this. I don't want to put all the values. Negative 1, negative 2, negative 3. This graph is actually something like this. It goes like this. Correct? Then remember, if I gave you a square root function and I ask you to find the domain, always set the radicand, or in a simple language, whatever the expression is under the square root sign, set it greater equal to 0, solve it, and easily you can find the domain. I will do one more example of these for you. Y equals square root of 8 minus x. Look at this. Find the domain, right? Easy. 8 minus x greater equals 0. Set it like this. Subtract 8 from both sides. These two cancels out. Negative x greater equal negative 8. Divide both sides by negative 1. You are a good student. I know every time that you divide an inequality by negative number, you flip the symbol, right? Then x less than equal 8. Number line here 8. Less than equal 8. You go this way. To where? To negative infinity. Then your domain is from negative infinity, comma 8 bracket. That's your domain. Very easy. And if you graph this, I don't know the exact graph. I'm not asking you to graph. When we start graphing, definitely you will graph. The graph something will be like this. This is 8. And the graph opens this way. Goes this way. Even you are not going to positive numbers. You are going to negative numbers. Correct? Enough examples? The next is how to find the domain of some rational functions. For example, y equals x plus 2 over x minus 3. Find the domain. to find the domain of rational functions, always set your denominator, which is x minus 3, equal to 0. Even in some classes, I tell my students, do this. Not equal to 0. But, of course, in your book, they will say set it equal to 0, not this way, not equal to 0, because that will be looking really crazy for you. What is this? I never did this, correct? Not this. Set it equal to 0, but remember, I will explain why I want to put that line too. Solve this. But remember, when you are dealing with rational functions, always set the denominator equal to 0. I don't care about numerator. I'm looking to find the restriction. Why I set it equal to 0? Because I want to find my restriction. And what restriction means? Restriction means the number that if you plug in that number to the denominator, or numbers maybe, and some of them, it changed the denominator to 0. And definitely, immediately we know that we cannot have this. A number over 0 is undefined for us, correct? Or later we will explain it's a vertical asymptote. Correct? Later. Maybe some of you already know I'm talking about vertical asymptote. But for time being, I call it a restriction. Restriction means the number that changes the denominator 0. You cannot have that number there because we have no answer for that. That's why you set equal to 0. Now solve it. Add 3 to both sides. These two cancels out. X equal 3. That's why I'm use this sign. X cannot take 3. But it can take all other numbers. All other numbers. Correct? That's why you get here a restriction. Now, if you draw number line, be careful with this because you're writing domain. Mark somewhere as a 3. Remember, for this sign, not equal, we always use an open circle. X cannot take only and only 3, but X can take all these values. On the right side of 3, I can add 4. 4 minus 3 gives me 1, correct? And X can also take all the values on the left side of 3. I can plug in these values too. Correct? Then how to write the domain? Here I have negative infinity. Here I have positive infinity. Parentheses, negative infinity. To where? To 3. What I'm using for open circle? For open circle, I'm using a parentheses. Then another part of the graph, parentheses 3 to where? To infinity. Connect these two with U. That's your domain. That's the domain of that function. Another example from your book. Find the domain. S equals 1 over t squared minus 60 minus 7. A position function. We call position function S, and t is time. Position is a function of time. Do you see in this example? I teach you a little bit physics. Position is a function of time. Correct? But I don't care about that part. Let's find the domain for this function. Find the domain. Set the denominator equal to 0. T squared minus 60 minus 7 equals 0. Can we factor? If yes, factor. If not, quadratic formula. You know now different methods, maybe completing a square if you have a lot of time, and solve it. T and T. Of course, the factors of 7 is 7 times 1, right? Then 7 and 1, correct? I need negative 6, then negative 6, positive 1, right? Negative 7, positive 1. T minus 7 equal to 0, it means T equal to 7. T plus 1 equal to 0, T is equal negative 1. These two numbers are actually your restrictions. To write the domain without doing a mistake, I always recommend draw this line. Some students, they try to avoid this. They want to just write, and sometimes they do mistake. It's not a big deal. It takes like a second or two to draw a line and put the numbers on it and see clearly what is your domain, correct? Here negative 1, draw an open circle around. Here is 7, draw a open circle around. This is your domain, this area. This part is your domain, and this part is your domain. Here you have infinity, here you have negative infinity. Look, the graph is actually the domain. It talks with you. If you put a little bit time and follow my instructions, you will not do a mistake on the quiz or on a test. Correct? Then parentheses, negative infinity to where? To negative 1. Then u, then from negative 1 to where? To 7. Then u from 7 to infinity. This is your domain. Correct? We talk about few types of these functions and how to find the domain of a function. There is another topic also in 3.1 or two topics. First, evaluating a function and also function notation. I will stop the lecture here and I'll do another video as a part 2 because I know I talk already 1 hour and 10 minutes in this long lecture. I don't want to put more on it. I'll separate that video from this. I'll stop the lecture and see you all back in 3.1 part 2.